The task of the final speaker is presumably to point out the errors of all of the ones who have spoken earlier. However, that would mean losing many friends. And so what I will do is actually point out a couple of errors of people who are not here. But to assure you of fair play, I have been in correspondence with both of them. Okay, so the question is, where was the photon? And now let's see if I can move this ahead. Has to do with a Mach-Zehnder Interferometer. Now, I start off not with the actual one I want to deal with, but with a simple Mach-Zehnder, where you know how it works. A light comes in, there's a beam splitter, and then the beam can follow either of two routes to a second beam splitter. And then depending on the phase difference, you get more counts in one detector or the other, or an equal number. In particular, you can arrange to get all of the counts, say, down in this detector. And when I use the word counts, I'm obviously referring to photons, right? Particles. Whereas the normal way you think about a Mach-Zehnder is that you sort of have a waves. You have two waves that can interfere. It's a little difficult to imagine how you can get a particle to interfere with itself. But anyway, let's start off in this simple system and say I detect a particle down here. Can you say anything about which arm of the interferometer it was in? And if you're wise, you will sort of not volunteer to discuss this particular point because there's something fishy about it. However, let me then go and express in quantum mechanical terms what it is that makes it difficult to say which arm of the interferometer you're in. We're doing quantum mechanics, so let me denote the upper arm by a quantum state. I always think of these in terms of spin a half or a qubit. Everything else is more complicated. Lower arm is ket 1, and I'll use this symbol for the projector, right? 0 inside square brackets is ket bra 0 is a projector onto that state. Similarly 1. And then the idea is that if I go through the beam splitter, I get some state psi, and there's a projector associated with that state formed in the usual way. For instance, the 0 might be plus c, the 1 might be minus c, the psi might correspond to the x direction. The crucial point is that the following assertion is nonsense. Particle was in state psi and in the upper arm. Why is that nonsense? That's nonsense because you have two projectors, a 0 and a psi, and they don't commute with each other. So the first sort of lesson in terms of realistic descriptions in quantum mechanics is to avoid cases where the projectors don't commute because that doesn't make sense. To put it in other words, when things don't commute, you are over into the border of quantum mechanics. Classical mechanics is where the projectors all commute, the ones you're interested in, for all practical purposes. So the non-commuting properties you cannot compare. Now, there are cases when you might want to talk about which arm the photon was in. For instance, if you introduce measurements inside the arm, then there are a couple of attitudes. One, which you find among the textbook writers, is nothing happens until a wave hits a detector, in which case there's a magical collapse. And as to what went on before, we don't say. We don't talk about that. On the other hand, experimental physicists, the ones I've talked to, do tend to have this attitude that when they set up their system to do a measurement, that it actually functioned. And if some detector goes off, it's probably because there was a photon traveling towards the detector. So So in this particular case, if I say where was the particle just before detection by detector D1, I hope that's the upper one, the response might be, well, it was here on its way towards that. And I would say that's a perfectly sensible response. And what we need to do in terms of discussions of quantum mechanics is explain to students why, in this case, such an answer is perfectly acceptable, despite the fact that we have some S going into this psi, and this projector with the psi doesn't commute with the projector 0 or the projector 1. Now, the first step in solving this is to say, well, start off with the identity operator, which is the sum of these two projectors 0 and 1. Identity is always the thing that tells you nothing. So you start off with no commitment, no knowledge, and then you split it up. You say, well, I will write this as sum of 0 plus 1, and then in the proper circumstances, you can make sense out of this and say, well, it was either 0 or it was 1 in the upper arm or in the lower arm. There are cases when you can do that. Another split up, by the way, is to say the identity is the psi, the superposed state, plus the identity minus psi, and this is also perfectly good, and in fact is what is implicitly used in textbook discussions. The trouble with those discussions is there are cases where you want to say the particle was here or there, and you can't do it because you're insisting on using that state. Well, let's go ahead. I continue. So, what are basic quantum principles? Well, the first principle is you have to have a framework to describe it. I've given you some examples. These are projective decompositions of the identity. You tell me which orthonormal basis you're interested in. Good, that's a framework. Second principle is the single framework rule, which says that you should not combine cases of frameworks where the projectors don't commute. That's nonsense. However, you as a physicist have liberty to, especially theoretical physicists, have liberty to choose whichever framework you prefer to use or make up many of them. The single framework rule is don't try and combine them. Then there are some additional rules, but these take me a quarter of a semester in the introductory course, and the organizers have not given me enough time to discuss it this afternoon. Now, here's the case I'm really interested in. It's the nested Mach-Zehnder Interferometer. So you see, it's similar to the previous one I showed you, except that on the upper arm, I have inserted a second Mach-Zehnder interferometer. So I've interrupted the upper arm. This is why it's called nested. Furthermore, in the case of interest to us, I apologize for non-fancy slides here and no colors, but I've tried to make the point that these two additional beam splitters are arranged and phases are arranged. So if light comes in here in the D, it moves through and it goes out again in the channel I've marked H. That's very important for the following discussion. And then okay, well, I think I move on to the next transparency here. Yes. So the question before the house is, we have this nested Mach-Zehnder. A photon will enter here in S. It will then be detected by D1, the detector down here. And what path did it follow going through the nested Mach-Zehnder? Can you tell me where it was inside, given these two pieces of data, where it entered and then where it was detected? And I will allow you for that purpose to assume that because it was detected here, it was earlier in the F channel, although, as I say, that's a liberty which not everyone will grant you. Let me then give you a plausible argument. I said it ended up here. Well, look, at this first beam splitter, it would either have gone in the D channel or it would have come down in A. If it had gone into D, then it moves through this inner Mach-Zehnder. It comes out there with probability 1, and it would be detected by D3. But it wasn't detected by D3, it was detected by D1. Therefore, it didn't take the upper route, but instead it went through the, through the lower route. Does this sound like a plausible explanation? Anybody willing to say they think it's plausible? I see at least one hand up. The rest of you should be less frightened, but I will go on. I will go on to have some further discussion. Now, the people with whom I agree or disagree. Sorry, let's go back here. Okay, so the question. Oops, I seem to be getting. Excuse me, I'm just inexperienced with this. So, photon was an A and not B plus C. Yes, this is a conclusion reached by Zuberi. That's Scully and Zuberi. He's a very distinguished professor at Texas A&M. And saying yes is part of an argument for a scheme of counterfactual communication which he and his friends have devised. It's a marvelous scheme because two parties manage to communicate with an optical fiber between them, but without sending any photons through the fiber. Do you believe this? Well, I'm misrepresenting it slightly. It's a negligible number of photons going through the fiber. Part of the argument to get there is he says, well, it was an A, so there was one detected in D1, which was an A, and therefore it was not in the B plus C system, and it was not in the B plus C system, it was not in C. So that's a key part of his argument. So let me continue. Oh, sorry, before showing the right answers, Lev Weidman is a well-known physicist at Tel Aviv University, Quantum Foundations. He says the particle was in A, and in B, and in C, but it wasn't in D, and it wasn't in E. That seems slightly problematical. Let me not explain how he reached that, but let me now give you the right answers in this case. Indeed, the photon was, the photon was an A, and it was never in the combination B plus C. So those who raised your hands earlier, you were in the right. Now, the next thing is that Zuberi gets partial credit because the particle was an A, but he reached the incorrect conclusion from this that it was not in C. He loses points. That conclusion is incorrect in a quantum mechanical world. And consequently, counterfactual communication is, in my opinion, in trouble. What about Weidman? He gets partial credit because the particle was not in D or in E. However, his A and B and C is not correct. Now, I have, so if the offensive preprint is already up. Okay, so these next things here were just to convince you that given the same circumstance, particle detected in D1, it was also in C. Remember, that was an A, but it's all, but I'm running out of time, fortunately, so I won't have to to go through this, and instead let me come to the closing comments. First, this Weidman versus Zuberi argument is something quite serious. It has been in various reputable journals. Nature has not accepted it thus far, but you probably recognize some of those other things. The basic issue here is what happens before a measurement takes place. That's the entire content has to do with that. This is something which the textbooks do a miserable job on, and I hope I'm not stepping on too many toes of textbook writers. I think that one can indeed explain things to students even in the introductory course. This means senior level at Carnegie, senior undergraduate at Carnegie Mellon. And students should be learning how to think about these problems. And the reason I say that, this meeting is quantum challenges. I think as time goes on, our students are going to run into lots of situations where they need to have an intuitive idea of what is going on before the measurements were made. And we need to teach them how to think about that in a way which doesn't get thoroughly tangled up in paradoxes. I wish I had had this sort of explanation when I was learning quantum mechanics, because at some point I was so confused that I thought maybe I was too stupid to be a physicist. That was before I heard the famous Feynman quote, "Nobody understands quantum mechanics." But I think there have been advances since Feynman, and I would like to see these put into the curriculum. So that's the end of my talk.